Good day, physical geographers. Hope you're enjoying Geography 112 here at Front Range. We're doing a little bit of a transition. Rather than talking about air movement and temperature heating up, we're going to move into atmospheric moisture. So we're kind of at a little bit of a shift in this class, and I think it's a good one. We're doing a little less foundation building and really talking about things that matter in terms of the concepts that we talked about. So should be fun. We actually in this chapter talk about one of my most favorite things, which I'm sure you'll see on questions for exams and those kind of things, and that really falls into essentially orographic lifting. What happens when certain fronts go over a mountain, or certain air masses, which we could talk about later in the slides, of parcel going over the mountains. What exactly happens? And it really explains a lot. Okay. Impact of atmospheric pressure on the landscape. So we have the hydrologic cycle. Remember we talked about the hydrosphere and all our spheres at the very beginning of this course. Water molecules, so what comprises that? As far as hydrogen and oxygen, certain properties of water, and essentially latent heat in the atmosphere. So we talked about heating and cooling 2 chapters ago, and we talked about air movement last chapter. So it's kind of getting all pulled together for us. And then in addition to what is water, there's different states of it. So evaporation, rates of evaporation, evapotranspiration, usually involving plant life, and measurements of humidity. So actual water vapor content, relative humidity, and we'll talk about those concepts in the condensation process. Okay, and then we also have adiabatic processes. So essentially what's happening with expansion and dry and saturated water, and how does that relate to temperature. And then we'll talk about some clouds, essentially some moisture compiled or getting built up in the atmosphere, fog, dew, and then clouds and climate change. Okay. And then as far as the air movements, we talked about clouds. We have atmospheric stability. So is it going to move or is it not going to move? Is that what we mean by stable, or does it mean that it's stable, that we will have some movement, but essentially it won't bring us weather that we don't desire? What's that mean? The precipitation, the whole process, forms of precipitation, atmospheric lifting and precipitation, convective and orographic. The last two are I always find very fascinating. Okay, so frontal lifting, convergent lifting, we also have that. Global distribution of precipitation by regions, seasons, and that varies. We have some good maps of that. Sources of acid precipitation, which is nitrogen oxide and sulfur oxides. Basically getting contained or carried through water vapor, water droplets. Okay, so here we go. Water is most of the widespread on the Earth's surface, 70%. So if we pulled up a globe and we looked at it, we would see that most of the globe is water. We have the hydrologic cycle. So what carries water? Liquid water evaporates in the air, condenses the liquid or solid state, and returns in precipitation. So that right here, we see that really the whole hydrologic cycle. Okay, the breakdown of water. Hydrogen and molecules. So we have what are called covalent bonds. O has a slightly negative charge, H positive, which allows them to bond or stick together. So we're getting into some core chemistry, the composition of water. Okay. And it has certain properties. Liquidity, as far as being able to flow. It can expand, so it can become a solid at a cold temperature. It has surface tension, so essentially can protect itself, if you will, like a bead. And that's how we have water droplets. For instance, a water droplet flowing down a windshield on a car or on a window in a building or a house, what have you. Okay. And then capillarity, which essentially lets it flow through the surface tension, lets it throw through cracks, rocks, those kind of things, which is essentially how we have the part of the hydrologic cycle essentially drains into the ocean, right? So we talked about condensation, advection, precipitation. There's subsurface flow and surface runoff. Both of those are essentially related to capillarity. Okay, so phase changes. So it can be a gas, it can be a liquid, it can be a solid. So these are each one of those. Evaporation, going to water vapor. Freezing to ice, which is a solid. Condensation, water vapor, essentially going to liquid, and then it could be deposited or basically flow. And essentially, we could also have the exchange through different types of heat mechanisms for each one of those. Okay. So each one of those heat mechanisms can be defined. How much energy does it take to change states? So when we talk about states, solid, gas, and liquid. So we have defined energy for each one of those. Latent heat of melting, evaporation, vaporization. So each one of those states can move to another state, and there's a defined amount of energy that it takes to change that. That's what each of these latent heats are. Latent heat of vaporization, evaporation, and of melting. As far as the phase changes, releasing energy can also happen. So we can have latent heat of fusion, latent heat of condensation. So it can work both ways. Energy can be gained or lost. Okay, so latent heat in the atmosphere. Evaporation can cool, which energy gets stored. Condensation, energy gets released. Very, very important. We'll see that again. Okay, so vapor pressure exerted by water vapor in the air. So air temperature has a maximum that it can basically exert. Saturation, how much water can be held in the air. So that's all measured by relative humidity. So at a certain temperature, the air can only hold so much water. If it becomes saturated, at that point, we have condensation, which could be in the form of rain, hail, sleet. Could be all kinds of things. Could be snow. We're in Colorado, so definitely have to say that one. And we have evapotranspiration, so soil and plants basically carrying moisture, and I kind of look at it as it kind of sets it up to evaporate easier. It's kind of the way I look at it. But plants give up moisture through what is called transpiration. So through various openings, pores, offerings that could be their external part of the plant, leaves, branches, those kind of things. Moisture could be offered up then. Measurement of humidity, absolute humidity. Okay, so what is the actual humidity for a given volume of air? So what is it even possible, or how much is even possible to be held in moisture in there? And specific humidity is more of a finite definition. It's the mass of vapor for a given mass air. So that's actually a calculation, if you will, on reality. And then vapor pressure contributing water vapor to the total atmospheric pressure. So we talked about there's a limit on vapor pressure also. So relative humidity. So how much moisture is in the air compared to what the air can hold? That's all relative humidity is. So if the relative humidity is 50%, the air holds 50 or half of what it can't possibly hold. If the relative humidity gets high, there's a very high chance for rain, sleet, hail, snow, that kind of stuff. Water vapor capacity is how much it can be held at a given temperature. These things should be pretty straightforward with what we worked on in the last few chapters. The dew point temperature, so that's essentially what temperature must it cool to reach saturation. So a dew point is essentially how cold will it get before you see a bunch of dewdrops or a bunch of moisture on the grass in the morning. Okay? hopefully that's really clear to us. Okay, we're going to start moving pretty quick here. Condensation nuclei, particles that serve as collection points for water molecules. So essentially, what does the water molecule go on? We talk about that with snow often. Has to have something that it actually goes on. Super saturated, where things are so saturated they don't have a place to go anymore. Super cold, same kind of thing. Things are so cold that they basically don't have a way to be staged anymore, which promotes the growth of ice. And then we have calculations for this cooling and heating we just talked about on the previous slide. So we have adiabatic cooling, and then we have adiabatic heating. So at what rate for a specific mass of air does it take for air to rise and cool, right? So essentially we see 5.5 degrees per 1,000 feet, the dry adiabatic rate. Okay, saturated adiabatic rate, notice the rate's a little cooler. So if it's saturated, meaning there's more moisture in the air, it's not gonna change in temperature as much, right? That fits in. This is a little bit advanced, but that fits into our concept of land heating up and cooling down faster than water. So all we're saying in saturated and dry adiabatic rates, which you could say dry and wet being saturated, all we're saying is the more water or more moisture there is in it, the less likely the temperature is going to move. Okay, so we could tie that into our example of San Diego, where the temperature doesn't move that much because land heats up and cools down more than water. Water is basically, when it comes to temperature, water is an anchor. It's resistant to temperature change. Here's a great example, almost the orographic effect. So we see is the air parcel is moving up, temperature's dropping. Once it comes over the mountains, it has room to expand. It starts heating up. Clouds, crystals forming, ice, classifying clouds, cirrus, wispy ice crystals, stratus, great. Cumulus, very large. Cumulus means precipitation, so big rain clouds. Then we have different clouds here, low, middle, high. Cumulonimbus, the ones that billow, go up really high on the far right. Fog, geography of fog, this is where we have fog existing where precipitation is persistent. Radiation fog, advection upslope. You can see pictures of those right here. Radiation moving, advection going to the side, upslope, we see on the mountains sometimes, and then evaporation. Okay. Now I want to get into atmospheric stability. So stability can mean a lot of different things. It could mean lack of a storm. In our case, it means, is it going to move up and down or move a lot, right? So if it's non-buoyant, it's not going to be moved as much. So that's what we really mean by stable air. So unstable air is buoyant, meaning it can rise and external forces can be imposed on it easily. We have a high pressure cell, which is usually warmer weather. We have stable air, and then unstable is usually a cold front or a low pressure cell. Okay, so ways we can determine stability: temperature measurements, environmental lapse rate. We can basically determine adiabatic rates of rising air, so we can see how much it's changing and how much moisture is in there compared to what it can hold. We talked about wet and dry adiabatic elapse rates. And then precipitation. We see a lot of that in Colorado, don't we? Okay, so precipitation, different forms of precipitation, how hail's formed, updrafts within a large billowing cloud, which we talked before as far as being cumulonimbus. Then we have convective lifting. And then we have orographic lifting, which is usually moving over a mountain. So let's spend a second on convective lifting. So as air rises, it cools. So we see the air rising, cooling off, and essentially enabling a storm. orographic, we essentially